All right. Okay. Hi everyone. So I know if you're like following the this is very loud. I don't know if you're following the news or studying for midterms or something. But you know, machine learning basically won all the Nobel Prizes in the last 2 days. So BME is now canceled. Physics is now canceled. It's all MI from now on. Right. So yeah, I have this slide from Scott Aronson. This is from a while ago, but true as ever. So I wanted to take a few minutes, and I will teach it the way I teach it usually. It's in principle on the midterm or whatever. I want to teach you something from Jeff Hinton's course, which was actually in the Nobel Prize citation. I think I can explain it. So part of why I can explain it, of course, the reason Jeff Hinton, I would assume, got the prize is that he brought about, in large part, the age of AI that we currently see. But the citation is actually for the Nobel Prize in Physics. It's actually for a very specific thing. And it's for developing computational models of how data might be stored using networks. So that work was started by John Hopfield, after whom the Hopfield nets are named. And it was further developed by Jeff Hinton and students. So what I want to tell you about, so this is Jeff Hinton's 2005 course. If you want to watch everything that's available now, it's very good. I think, so I had the privilege of taking the in-person course with Jeff Hinton. So the Coursera course is he's a little bit mechanical, but I think the charisma still goes through. And I strongly recommend checking it out. He tried making it accessible, so that's available in the slides here, isn't it? Okay. Even better live, but unfortunately, the live lecture, I have it in my memory, but you will not get to experience it. So I took the course. So this is CSC 321 with Jeff Hinton in 2005. Back then on the PY portal, there were 2 or 3 AI job postings. I got one of those jobs. I was actually the second person in the list. They interviewed, they made the list. I was second, but their first choice, I guess, got another offer and went elsewhere. So I got the job, and right after taking the course with Jeff Hinton, actually went to Seiko Epson, and we implemented some of his stuff in the Epson scanner drivers. And that led to, my first patent. And also, it's actually still in the driver. If you want to buy an Epson scanner, very good. Okay. So, and then it happened that 10 years after I took the course, I actually had the privilege of teaching it the one time. So that was nice. I did not teach this topic because it's a little bit outdated. It was outdated even when I was teaching it back then. But that's what's in the Nobel Prize citation. So I will tell you about hop-fill nets using Jeff Hinton's slides. So if you don't like them, well, I guess take it up with the Nobel Prize committee. So hop-fill nets. So ignore this. So it's where is the picture? So yeah, so what I like, so we want the picture. So essentially it's a way about thinking. Sorry, you have a question? Yes. So and potentially. So I will tell you, I'm teaching it for real. So obviously kind of the slide that is skipped, you don't need to know about. But what I teach, I'm teaching it for real. So quiet down and listen. So the problem that they tried to address was how to store memories kind of the way that they're stored in the brain. In the computer, of course, memories are stored basically as lists, right? So you imagine that you have some data, you hear some words, you see some pixels, and then if you're a computer, what you see is a list of numbers. And that somehow encodes any kind of information that you want. So I think everyone knows that you can encode images this way, right? So you can just record the brightness of the pixel at the top, and then the brightness of the pixel to the right of it, the brightness of the pixel to the right of it, and so on. And this is how you would store, for example, an image. But that's not how humans work, right? So a typical student, they look at the slide, they don't remember every pixel. They don't even remember every letter. They don't remember anything. But to be serious about it, so somehow what you remember, if you perceive an idea or you read about it, you somehow store some kind of vague notion of the essence of what you saw, hopefully, not every pixel. And the hop-fill net was an attempt to try to do something that would look kind of like that. It took the idea from physics, from material science, of how materials work, and tried to apply it to, maybe the brain works like that. It probably does not. It was just the first attempt. So this is an example of a hop-fill net. So what you have here is a bunch of nodes. So every circle is a node. And then each node can be 0 or it can be 1. And then nodes can be connected to each other or not. So for example, this node has a connection here, but this node is not connected to here. Make sense? So every connection has what's called a weight that's associated with it. So for example, the weight of this connection is 3. Okay. So the idea would be that the nodes here, so the white circles kind of represent something like neurons in the brain. It's not really like what the brain works like. It's an idea of how to bring physics over to something that resembles something, the first development, right? So each node, 0, 1, the memory, or all the memories, are the weights. So the weights, the numbers like 3, 2, -1, 3, and so on, those represent all the memories that this hop-fill net has. All right. So far, what I told you is this is all the memories, and it's a bunch of numbers. Now what I'm going to tell you is how those numbers are actually able to store memories, to store data, kind of approximately. So the way it works is via the energy function. So the energy function can have many forms. I'll explain this one. So what you do is, if two nodes are connected, then you add Si times Sj times Wij O minus 2e. There is also a BI that's associated with every node, every neuron. So looking at this again, if you have a value for each neuron, so for example, if this is 1, this is 0, this is 1, 1, 1, that's associated with an energy. Make sense? It shouldn't really make sense, but that's what we've done so far. Yes. I still haven't said how memories work, so I'm setting up the framework. So you compute the energy by using this form. So if you have, particular values for the neurons, you can compute the energy. Okay. The way you compute the energy is, for example, like this. Right. So if you know the SI is the value of the ith node. Sj is the value of the jth node. And then Wij is the value of the connection between I and j. So for example, if the value here is 1 and the value here is 1, and this is Si and this is Sj, then the contribution to the energy would be minus 1 times 1 times 2. Yeah? Yes.
Mention that minus sigma is only worth the highest one.
Well, so it's not me, it's Hinton. So this is what you're referring to is the smaller thing here. So what we're trying to do is just every possible combination of phi and j, and we're trying not to repeat ourselves, right? So this is just saying every possible I and j, but so that we don't repeat ourselves, we're restricted to I is always smaller than j. Yeah? Yeah. What BI, so BI, I don't really want to get into it, but since you asked, so BI is a value that's associated with every number I that you can set to whatever in the same way that you can set W to whatever. Okay, but so you can ignore this term. I'm sorry I didn't, something came up and I didn't have time to make better slides than Jeff Hinton, but, yeah, so you can ignore this term, focus on this one. So just imagine that all the b's are 0, it's fine. Okay. So, all right. So if you know the values of each neuron, you can compute the energy value. The idea is you store memories by saying, if you want to retrieve a memory, you find a combination of values for the nodes that's as small as possible. And that's a memory. If you want to insert a new memory, you're saying, I want to adjust the weights. So I want to adjust, the 3, the 2, the -1, and so on, in such a way that next time, if I try to minimize the energy by finding a value of the nodes, I will also find that the new memory corresponds to an energy minimum. All right. So that's a Hopfield net. So it tries to store memories in this kind of approximate way. Of course, if you want to minimize this energy, there can be a lot of ways to choose the values of S such that the energy function is minimized for a given set of weights. So a Hopfield net is going to be able to store approximately, not exactly, implicitly multiple combinations of S by just making it so that if you have this network, you can and you find a combination of values of f that makes the energy small, that should be a memory. You would also prefer, of course, that if you do find a good minimum, that it's a real memory, not a hallucination. All of those things are a problem. It doesn't work very well. It was the first attempt by Hopfield to do something like that. And then Jeff Hinton kind of developed this idea into what's called restricted Boltzmann machines, which are essentially this, but more complicated and worked much better. The history of it is that for a time, deep neural networks, so the technology that underlies image recognition today, stuff like ChatGPT, they were very difficult to set up. And there was a trick to get around those difficulties by using restricted Boltzmann machines. That was around 2005, 2007-ish. Since then, people found more straightforward and more effective ways of doing the same thing. So people don't often use restricted Boltzmann machines, or certainly not Hopfield nets, but it kind of gives you an idea of you can store memories in this approximate way, but by using this kind of network that resembles a little bit neurons in the brain that are connected to each other. And historically, that contributed in multiple ways. So it demonstrated that you can use this network idea in order to store data. That was not obvious. It also contributed, like I said, around 2005, 2007 to the state of the art in terms of training deep neural networks. Yes.
The purpose of finding to get the minimum energy, like what does that have to do with memory?
So the idea is you store memories by setting the weights in such a way that the minima of the energy correspond to real memory. Okay, so the way you store memories is by figuring out the combination of weights such that if you try to find values for the nodes such that the energy is minimized, you get minima that corresponds to real memories. Is that kind of making sense anyway? Yeah. So you have data, and the data would be, the value of this is 1, 0, 1, 0, 1. It's encoding something here. And then you have a bunch of data that you want the network to represent, meaning that you want for the minima to correspond to data that you've actually seen. And then you also want it to be the case that if you find an energy minimum, that it would be something like what you have in your actual data and not something completely different. Okay, yes.
What's the benefit of using this over non-recurrent schema language?
I mean, again, this is like 70s, so like it doesn't work very well. It's more a historical development, which is, in the Nobel Prize citation from yesterday. So I wanted to tell you about it. Okay, other questions? Okay. Yeah, so I think we're all, I'm sure like the MI major is going to grow. We are all enjoying the glow. Jeff Hinton got the call from the Nobel Committee. I got an email from U of T Media Relation on whether I would serve as an expert on the breaking news that Jeff Hinton got a Nobel Prize. So, like you get what you get. I was waiting for the call from the Nobel Committee. Somehow it didn't come. So okay. Questions about any of this? All right. Okay. So this is just an introduction. So I did say it's testable material, and it is. So what is testable about this material, just to not freak you out? So what is testable about this material is what does, so I could ask, what does this kind of sum correspond to in terms of the picture, in terms of a picture over here, right? And then one question I would imagine asking is, like, here is a very small network, so just like one node connected to another node, one neuron connected to another neuron, what minimizes this? What's the answer? Anyone? So if I have this kind of network, and the weight is, let's say, 2.1. So this is like circle connected, and the weight is 2.1. The values can be 1 or 0, like we said. So what minimizes this? Zeros, right? Okay. So it gets more interesting and more complicated if you have a larger network. Yes. Say again? So if there's negative weights, then yeah. Okay. All right. Questions about this? Sorry, so the question was, I didn't repeat it. What would a 1 ever minimize? And the answer was, here the weight was positive, so you want zeros. But if the weight had been negative, then you could make it more negative, but by making it 1, 1. Yes. I mean, you can set it up every which way, to be honest. Yeah. So the nodes are restricted to 0, 1 or to -1, 0, 1, depending on the setting. And then the weights can be any real number. Yes. Sorry, I heard about alphabet. I'm not going to make you repeat it. Maybe we can talk after lecture. I think what you were asking is, can't you just push it to negative infinity? And the answer is, well, if you have both positive weights and negative weights, and so both, if you have both positive weights and negative weights here, then you become constrained because you put in a 1 and in one term, so in one product of SI times SJ, it pushes things up, and then another, it pushes things down because the W could be positive in one connection, negative in another connection. So you constrain it that way. Does that make sense? Yeah. Right. You're correct, and I was thinking that, and I was hoping nobody would know this. So what you pointed out is that in this formula, actually, you want to so if you want to minimize the energy, that means that you want to maximize the sum of SI, SJ, WIJ. Of course, you can just flip the sign, and that would also work. But you're correct. Thank you. Okay. Other questions? All right. Okay. I'll try to make a video, just like in case other people elsewhere in the world who didn't have the privilege of taking CSE 321 can see it. It might be a little bit better, but I thought, today I didn't have time to prepare a good one, but I hope that that was kind of interesting. Okay. What's Discord saying? Hello. Okay. Yeah, I kind of feel that my best shot at a Nobel is in literature for, posting on Discord or some contributions to Discord. Yes. Will you have? Sorry, I really can't hear it. Yeah. No, so the question was, do you need to know about the second half of the slide? And the answer is no. Like what they said is what you need to know. It's kind of, and I'm also not going to ask you to memorize formulas. There will be an exercise in next week's lab that's going to make clear what you need. Okay. Alright. So, back to work. So, I want to talk about, printing. This is passwords. So I want to talk about printing combinations of numbers and letters. So if you remember, if you do a nested loop, so something like for I in range 3, and then for j in range, let's say 4, you print something like I and j. What you get is 0, and then 0 with 0, 1, 2, 3 attached, and then 1 with 0, 1, 2, 3 attached, and so on. Yeah. So let's count. So here we're saying for I in range 3, so that means that I is for 0, and then it's 1, and then it's 2. So this is the i's. And then j ranges from 0 to 3. So j goes 0, 1, 2, 3, 0, 1, 2, 3, and so on. So one way of saying what it is that we're doing here is printing all the combinations of zero, 1, 2 with 0, 1, 2, 3, 4. Okay, so we're saying 0, and then all the combinations of 0 with the j's go 0, 1, 2, 3. Sorry, 0, 1, 2, 3. And then I is 1. And again, we're saying print 1 together with all the possible j's. The possible j's are 0, 1, 2, 3. And then 2 with all the j's, 0, 1, 2, 3. Make sense? Questions about, are you with me? Okay. Are you not with me? All right. So can we make it more interesting? Well, I can say I want not just all the combinations of 0, 1, 2, 3 and 0, 1, 2. I also want to add a letter. Like so. How do I do that? Well, here right now for given I and j, I just print ij. But I could say I have my ij. So I have my I equal to 1 and j equals to 3. And then when I is 1 and j is 3, I want to print 13e, 13n, 13g. Yeah. So how do I do that? Well, I write another loop. So I'll say for letter in, so here it's letters, so I'll just make a list. So I'll say letter is going to be E, and then letter is going to be N, and then letter is going to be G. I'll print not just ij, but ij together with the letter. Here I can say, at this point, I is something, j is something. So maybe I is 2 and j is 1. And then for 2, 1, I want to print E and G. So I can say, so I'm just going to say, like, every time that I set on a particular I and j, I'll just say, I'm about to print that together with all kinds of letters. So that looks like this. right? So instead of just printing 0, 0, 0, 1, 0, 2, and so on, here I'm saying for example, 0, 2, first print that you're about to print all combinations of 0, 2, and then a letter, and then you just do it. So that's this part. And the way to think about it is there's nothing like it is, you know, a loop within a loop within a loop, but there's nothing like too exciting going on there. You're just saying over here in the highlighted block, I and j are not going to change. And the highlighted block is just saying print all the same I and j's and then change out those. Make sense? And then you say, well, okay, how does it work? And the answer is, well, if you think about this block, I is fixed, I is not changing inside this block. What's changing is j and the left. So if you think about this block, where is it? It's this thing initially, what you see on the screen, right? So it's 0, 0e, 0, 0n, and so on, up to 0, 3g. When I is 0, that is what gets printed. When I is 1, that is what gets printed. Right? And if you think about it like this, so if you think about just a highlighted block, you don't need to think about, oh, like what's going on with the 3 nested loops there, because inside the block, it's just 2 nested loops, and we've done lots of examples like that. Right? And then you're saying, well, I'm just going to do this. If I is equal to 1, that should kind of make sense. We're just printing number, letter, and then I is just fixed. It's all the same. It's always 1. And then what we're saying, well, now that we understood this, well, set I to 0, and then set I to 1, and then set I to 2. Okay, questions about this? Who's not with me? Seeing no objections. So let's say that I want to print all the possible passwords. So continuing the example of like trying to break into a system, like for example, the network of the Nobel Prize, and just award all the prize, steal all the prizes and send them to machine learning. You don't need to do that; they do it anyway for free. But let's say that we want to print out all the possible 5-letter combination. So let's not do like unethical hacking. Let's imagine that you're just like very bad at Wordle and you want to just list all the possible guesses and try everything, right? Let's say of A, B, C, D. So how would you do it? Well, it's the same technique, right? So here we printed out all the combinations of number, letter. What we want here is just all the combinations of letter. Right? So let's do that. So I'll say for letter 1 I'll set alphabet to be this. And then I'll say for letter 2 in alphabet. So let me stop here and just do 2 letters. That should hopefully be more straightforward. So I'll just do letter 1 plus letter 2. So before I had commas, here I'm just sticking letter 1 and letter 2 together, right? So it would be like AA, AB, AC, AD, and so on. Let's run this. So that's like this. Is that making sense to people? This is just all the combinations of ABCD with ABCD. Let's do 3 letters now. So that is now all the combinations of 3 letters. Why is that? Well, because we're saying when letter 1 is A, just do all the combinations of letters. That's this part over here. Right? So here, letter 1 is always the same. Inside the block, letter 1 is always the same. And then we vary letter 2 plus letter 3 to everything that's possible. Yeah. All right. So let's just do it for 5 now instead of 3. And there you are, all the possible things. If you used up all the letters except A, B, C, D, and they were all gray, you're trying to find the Wordle guess. And those are all the possible Wordle guesses. I play Wordle once a week. We have like dinner with one of my friends every week, and we start by playing Wordle. It's a fun tradition. So I don't have a streak, but you know. Okay. Questions about this? Yeah.
So letter 1, 2, 3, 4, 5, we're all variables. Why you can make that.
Yes. Well, they're variables that are strings, right? So their value is A, B, C, D. So that is why you can put them together using plus, because you can say something like, you know, A plus C, and that's going to be AC. In that, yeah. Indeed, there is. The question was, can I do, can I do the entire alphabet? Yes, I can. I'll show you later. Another question that you might have asked is there a way to do, all the possible 10-letter words without writing out 10 for loops? And the answer is yes, there is a way, but you won't find out until about week 11. Yeah. Sorry, I think you were first. Yeah. Yeah, so if you remember, you can iterate through a list. So this is not new syntax. This is syntax from the other day. You can iterate through a list like so, right? So if the list is, okay, so Hinton and Hassabis is the DeepMind guy, and then Vance is also on the list. Then you can say for E in L, print E. And that's going to print Hinton and then Hassabis. And so Hassabis is the DeepMind guy who won the Nobel yesterday. And then Vance is next year. So what you get is E is first Hinton and then Hassabis and then Vance. Okay. So that is the same mechanism that I'm using here. So I'm saying for letter 1 in alphabet. So that means that letter 1 is going to be A, and then B, and then C, and then D. Yeah. We don't have, what do you mean? Okay, I see what you're asking. So the way it works, so let's go back to just this part. So I'll copy and paste. So there is like two senses in which you have, so you have 4 possible letters, A, B, C, D, but you want 5-letter words. So that means that one of the letters is going to repeat, right? So here, if you just run this, so highlight, Alt Enter, what you get is A, B, C, D. And then letter 5 is the letter in position 5. Right? Okay. I think there was a question Here, no? Anything else? Yes.
So the final value of letter one should all be D, right?
It is true that if you ask what the value of letter 5 is right now, it's going to be D. In fact, the last thing that got printed is all D's, which means that the last time that line 12 was run, all of them were D's. So if you ask about any of them, they would be D. Yeah. Yes. That's what?
5/8.
5/8. Yeah, that's the very first thing. So initially you're saying for letter 1 in alphabet, and letter 1 is A, and for letter 2 in alphabet, letter 1 so when you're first running this, letter 1 is A and letter 2 is A. And then you're first running this, they're all 3 A's. So yeah, initially they're A's. So that's actually a good question. So let's trace this kind of thing. So I'll say for X in 1, 2, 3, for Y in 4, 5, and I'll say print XY. So what does it print? All the combinations of 1, 2, 3, and 4, 5. Right, so 1 and then 4, 5, 2 and then 4, 5, 3 and then 4, 5. So if I put a breakpoint here and run it, so the first time that I enter this loop, X is 1. And now when X is 1, I'm about to run this. So initially Y is going to be 4. And I'll print 1, 4, and then Y is going to become 5. X is still 1. And I'll print 1, 5. And now this loop is done. This loop was doing X is fixed to 1 to 1, and then Y goes 4 and then 5. And now we're back here. So X was 1, and now X is about to become 2. And now we're doing 2, 4, 2, 5. So 2 is fixed, and we're doing 4, 5. So your question was, does 1, 1, 1 ever appear? That's the same question as like, does 1, 4 appear? Well, yes, that's the first thing that happens. It's 1 and then 4. Okay, other questions? All right. So that's print all passwords. You can think about it as the way we thought about it, of like, you're fixing letter 1 and then letter 1 is fixed, just do everything with letter 1 fixed. Or you can think about it as a common pattern. If you want to enumerate all the possible combinations, that is how you do it if you have a limited number of combinations. You need to wait until about week 11, week 12, where we do a more advanced technique where it is actually possible to do all combinations for a very large number of letters or whatever without having to do a huge method. Okay. All right. So let's talk about nested lists. So a nested list just means a list that has lists as elements. You can write it like this, so that would resemble a matrix. But Python doesn't care about kind of the fact that you arranged it nicely like this. As far as Python is concerned, L1 and L2 are the same thing. Right. So, and what is L2? That would be the more usual notation. Well, L2 is a list whose first element is the list 1, 2, 3, and whose second element is the list 4, 5, 6. That is called a nested list. Nested means a thing within a thing. So how do you access elements of this? Well, if you have a list like this, so you might recognize the letters, but they're just elements. So if you say L at 1, that means you get element number 1 from the list L. So that's psi, the list that spells psi. Right? So that is L at 1. If you want to get a specific letter, so for example, you want to get the I, you can say, well, it's this list, and I want element number 2 from it. So L at 1 is this, and L at 1 and 2 is the I. Questions about this? So pretty straightforward. You will see, you might have seen already, have you seen matrix notation? No? Well, so someone gives me a thumbs up, but not most people. Have you seen matrix notation in ANSI? I mean, the answer is yes for everyone because you just have seen it now. So if you think about L1 as being the matrix, then you can say L1 at 0 is this guy, because first element of the first element of the first row, and then L1 at 1 at 0 is this guy, right? So L1 at 1 is 4, 5, 6, and then L1 at 1 at 0 is this guy. You write this. So L1 at 1 at 2, let's say, is 6. So this is like matrix notation, but with indices starting at 0. If you don't like indices starting at 0, you're going to love MATLAB because that is one base, that has one base index. Okay, questions about this? Does this make sense? Yeah. So the question is, what do the square brackets represent? And the answer is L1 at 1 is elements with index 1 in L1. So it's this element. And then you can say, I want element at index 2 in L1 at 1, and that would be 6. Make sense? So it's not new. It's just a use of accessing elements of lists where the elements themselves happen to be lists. All right. I feel like people have had enough. I will see you on Friday. I feel like we haven't had a quiz for a while. I wonder what's going to happen. Okay. All right. Okay. I'll see you. Bye.